Thank you all for attending, and I'm honored to be the first speaker here in sunny Southern California. There's no place I'd rather be to talk to you about my favorite topics in astronomy. So one is on learning about galaxies and especially the physics that drive how they evolve. And the second is the growing role of machine learning. And we know that this is a really pivotal time in astronomy and survey astronomy, with lots of large data sets coming up and a lot of attention for deep learning. And I believe that these fields are going to be really useful for supplementing, but not necessarily replacing targeted observations. So I'm John Wu, by the way. I'm a relatively new assistant astronomer at Space Telescope Science Institute. But I actually cut my teeth in my PhD doing targeted observations. So this is with radio interferometers in the far infrared and submillimeter, ranging to integral field spectroscopy in the near infrared and other wavelengths. These targeted observations really help us address the key questions in systems and galaxies that we want to understand better. But as we've seen in the past couple of years, there are also examples of the kinds of analyses that are now possible with brand new machine learning tools. And in fact, we've talked about this a lot in the past couple of weeks. So with Euclid, LSST, and Rubin coming up, I think that machine learning is going to be critical for making some of the next big discoveries. All right, so let's get started here with the structure of my talk. So first, I want to provide an overview of galaxy formation and evolution and how we might want to make better use of galaxy images. And in order to do that, we need to leverage all the information in the image domain. And so we're going to have to be familiar with tools of the trade, which are convolutional neural networks, or CNNs. And I'll show some scientific applications there. And then third, I want to present an exciting new method for discovering dwarf satellite galaxies in the very local universe, very low redshift universe, and present some new results there in future directions. So let's get started with the growth and evolution of galaxies. So we know that in the hierarchical collapse scenario of lambda CDM, that you have dark matter at early times in the universe collapsing under gravity into these structures called dark matter halos, and they continue to accrete matter. Right, so on the left here, you're seeing a snapshot of the cosmic web in the dark matter only simulation. But if you look at the baryons on the right here, it's evident that gas is actually accreting at the centers of these dark matter halos, and in there a galaxy is born. Right, this is through the condensation of stars from the cooling gas. And to sort of model this, I like to summarize this in a more abstract format. This is the growth of a galaxy, as a function of time in terms of its mass. So this is really the star formation history from early times to late times in the universe, or at some time of observation. And this rate of star formation is going to be tied to the matter accretion rate and the gas accretion rate. We also know physically that it's tied to this other curve that I've drawn here. This is this kind of pink-red curve, which is the chemical enrichment history, which tells us something about the rate of production of heavy elements over time. Naturally, these two are going to be connected to each other because we know that heavy elements are nucleosynthesized inside the stars that need to form from the cooling gas clouds. So physically, these two things are going to be related. All right, but as I said, I'm an observer. I care about things that we can observe. So maybe we want to look at the star formation rate at the time of observation, which is just that endpoint of the blue curve. We could, read off something about the stellar mass, or at least model that, which is the integral of the blue curve over cosmic time. And likewise, we can even say something about let's say the metallicity, which is related to the chemical enrichment history over time. Okay, this is a very crude model, but again, I'm just trying to put together some physically connected variables. Now, as I said, since these two curves are correlated, we also expect that their integrals are going to be correlated as well. And indeed, if we measure the masses and metallicities of over 100,000 galaxies, like the Sloan Digital Sky Survey did about 20 years ago, or with Christy Tremonti et al.'s seminal work, we find this nice scaling relation in astronomy. So these observations are showing that the stellar mass and the gas metallicity of galaxies, for 100,000 systems or so, is correlated. And of course, we can also use better statistical models. I think, again, people have talked a lot about these here, where you can use empirical models, better techniques to do things like, measure the star formation histories better, to, put together bathtub models or semi-analytic models. And altogether, we know that these advanced models are going to be very successful, right? We've come a long way since then in terms of like understanding the physical histories of these galaxies, and we don't need to just draw these simple curves. But hang on, we've been neglecting one of the most important characteristics of galaxies, in my opinion, which is their beautiful morphologies. And we know that galaxies come in all shapes and sizes, that there are complexities when you try to categorize them, but these are still connected to the physics that drive them. Right? The morphology really reveals the ongoing physical processes and the evolutionary state and history of a galaxy. And to make this point clear, I've got this really boring table here. This is just, 2 columns showing, a bunch of galaxies from DESI legacy imaging surveys that have the same R magnitude and G minus R color, right? Not very illuminative, but if we look at the images, we can see a lot more about what's happening in the galaxy, where the stars are forming, some imprint of, the tidal effects, their accretion, recent accretion, and other types of, physical processes that may be happening in the galaxies. And so what I'm trying to get at is that, the images, as complicated as they may be, contain a lot of rich information that we cannot afford to neglect, okay? So in order to do that, I'm going to have to start talking about how to make machines see, or convolutional neural networks. Now, I don't think I need to really explain this in great detail, but we do know that there's like this rough approximation of how neurons work that is probably not actually motivated by biology. But in any event, we know that you can design an artificial neuron which transmits some sort of signal through a neuron, and basically is sequentially put together in these so-called layers, which pass along signals. And so, artificial neurons kind of try to emulate this at the same way. So maybe you have some inputs, which are X's. These are just, numbers or vectors. And then you can basically take an inner product with the weights, which are just parameters of the neuron, add a bias term, and then pass it through some nonlinear activation function. This is just a very non-trivial transformation that a neural network will need to learn in order to represent, some sort of inputs in order to do some tasks. And in fact, yes, we can also stack together a whole bunch of these neural network layers, basically just sequences of neurons together in order to do some interesting output tasks. But specifically, I want to talk about the information in galaxy images. So we're going to want to look at convolutional layers. And so here, this is an input image, just shown as a 5x5 grid of pixels, right? It's just an array. And shown in white, we have a convolutional filter. This is actually, I don't know if this is white, but whatever color that is. This is a 3x3 matrix that's sort of, overlaid on top of the image. And this is going to search out for some sort of simple morphological feature. Okay. And so where the filter is similar to the underlying image or the weight parameters here, then the convolution should produce a large output. And in fact, that's what this tells you here, right? This number that is produced there is actually just a map, or basically starts to produce a map of how similar the input image is to the convolutional filter in question. Okay, and so what you have, if you apply a nonlinear activation at the end of all this, is again a map of features, or an activation map, as it's sometimes called. And then you can now take this map of features and treat this as an input image again, repeat the process, and learn more complicated representations of whatever astronomical input you're interested in. All right. So at the end of all this, you would expect to formulate, from simple representations in early layers to sort of later representations, maybe more high-level features of galaxies. And then ultimately, you kind of get this vector, which I'm just representing as like a bar chart. This is some high-dimensional abstract vector. In an ideal world, we would like it to represent something physical, like maybe how asymmetric the source is, or how many tight winding spirals there are, or whatever. But in reality, it's more complicated than that. We know that there's some nonlinear combination of these features that tell us something about the morphological content in these galaxy images, if that's what we're looking at. But whatever they may be, and we'll talk a little bit about methods to probe them in a bit, we want to be able to use them to make some sort of downstream prediction, okay? So again, training a CNN amounts to finding the parameters in this, not black box, but interrogatable box, on how to how to solve this problem. This is a supervised learning task as I've set it up. And indeed, it needs to learn a flexible representation of galaxy images, and you're not hard coding it. And so this is really how the advent of machine learning, I think, has transformed the sciences. It's transformed, basically our day-to-day lives in many ways. because data-driven techniques allow us to come up with those flexible representations of what we care to study. Alrighty, so scientifically though, this works really well. So we can train a CNN, as I've shown back in 2019, to estimate the gas phase metallicity of a galaxy directly from Sloan imaging. Okay, and this is way more accurate than we really thought it should be. We were able to pin down the gas phase metallicity to 0.085 dex, which is, really not a lot of scatter. And indeed, when we try to reconstruct the mass metallicity relation, and so here we've got the CNN predicted metallicities, really the y-axis here is predicted by the CNN in red, and then you also have the black curve, which is the measured metallicities from Sloan spectroscopy and based on another model. We found that this mass metallicity relation actually didn't add any extra scatter when we went to CNN predictions. In other words, we were able to bypass some of the things that we would typically learn in spectroscopy and try to attribute that to features that are found in the images. So I think what this is telling us is that, just as we expect some scatter in the mass metallicity relation to be explained by the star formation rate or perhaps some other physical parameter, right? This intrinsic scatter is not only here. There's actually another variable that might explain some of the scatter in that. What I think we're seeing here is that a neural network or convolutional neural network can extract morphological information that explains some of the scatter in the mass metallicity relation. So machine learning in this way is really telling us a bit about the physics of how galaxies are growing. It turns out that we can also go and estimate the neutral atomic hydrogen gas content in galaxies from images. And H1, neutral hydrogen, is the dominant phase of gas in low redshift galaxies. I spent a lot of time thinking about H1 during my PhD. And it really is telling you about the intermediate timescales of galaxies forming and continuing to grow. So now with CNNs, we can not only estimate the H1 gas mass, but we can also investigate which pixels in the underlying images are most important for making different kinds of predictions. So for example, if you look at gas pore predictions, for example, you can just condition a CNN to give you a gas pore prediction, and it will highlight the pixels it would have looked at in order to make such a prediction. In this case, both of these galaxies are actually gas rich, and in fact, this has a much higher likelihood. Approximately, you shouldn't interpret it as a true likelihood, but it is more willing to say that both these galaxies are gas rich. And indeed, if you look at, you condition on that particular classification, it will highlight the pixels that it thinks are most relevant. In all cases, this is aligning exactly with our intuition, right? It's illuminating these H2 regions out and, maybe the accreting or the tidal filaments of this galaxy here. And as well as out here, we're looking at the gas-rich disks as being the most important parts of the image. So again, this is giving us intuition of what a CNN is learning. And here's the fun part. So Josh and I, 2-3 years ago, decided to just go out and predict the entire STSCI spectrum from Pan-STARRS imaging of a whole bunch of galaxies. And it does ridiculously well. I mean, we've taken, spectra, which are de-redshifted, and then actually compressed down into a few latent variables. So there is that caveat, and can be reconstructed into spectra. But from the images, you can see the observed spectra, which are in black, versus the predicted spectra from a trained convolutional neural network match very, very well. In fact, the only place where it doesn't really match is towards the U-band, because we actually, with Pan-STARRS, you don't have any U-band imaging, so it has no anchor point there. But otherwise, this works extremely well, and you might be very skeptical, like I definitely was when we first started seeing this, thinking, this is kind of ridiculous, like how far can we push this? And around the same time, as the story goes, we were all on social media. One of my collaborators, Bennett Huerta, was asking around on social media if anybody had a spectrum of this particular galaxy. So this is apparently right outside the SDSS footprint, so there's no spectrum taken of it, even though it's relatively bright. And I mean, like, why do you need a spectrum in this thing? I don't know. It's like his favorite galaxy. It's cool. There's a lot of nice press releases from this Hubble imaging. But as you can also kind of see, it's a very, very large spiral galaxy. It's in a very isolated environment. It seems to have a pretty quiet merger history. And so we were all curious about whether there is a supermassive black hole at the center of this galaxy. It seems to have an undersized bulge and all these kind of peculiarities with it. So we wanted to know, what is the excitation state of the center of this galaxy? So we grabbed an image cutout and did our usual trick, predicted its spectrum, and we found that it should probably have a weak AGN. Great. So the CNN prediction, indeed, is if you look at a BPT diagram, basically looking at line ratios in the optical spectrum, we predicted predicted an optical spectrum, harvested its characteristics, and basically found that it should have this AGN based on the Sloan 3 arcsecond fiber aperture. We then actually followed up with additional observations and also digitized some spectra taken back in the 80s at varying aperture sizes. And what we found, interestingly enough, is that indeed this galaxy does harbor an AGN, but also the 3 arcsecond fiber is nicely positioned between these two, which is exactly what you would expect if star formation is diluting the signal on larger apertures, but the AGN at smaller scales is actually shining through. And so I think what we're finding is that the CNN is working, and even in this outlier example, it's telling us something, it's learning something about both the observational data that it's trained on, as well as the underlying connection between the galaxy's image properties and its physical state. Okay, I have 5 minutes left, so I'm going to go on to the final bit. But as a summary, of course, we basically know that we can learn lots about galaxies. We should go out and do that. But of course, there's more to learn about, how galaxies are forming and evolving, and some of that involves, pushing the frontiers of what we can even detect. And so here's a fun challenge, which is to pick out all of the dwarf galaxies in this image. And so, I'll just kind of motivate the question here, which is that there are satellite dwarf galaxies and they've had a tough life, right? They're already really faint. It's difficult to find them, but they're easily destroyed and their growth is totally stunted by all sorts of physical processes. So from cosmic reionization to star formation feedback inside that galaxy to ram pressure stripping from the hot halo that it might be falling into, or maybe tidal forces that are shearing them apart. And it's no wonder that they're great for comparisons to all kinds of physical theories. So again, I don't have time to really get into the details, but you have the missing satellites problem, you have the too big to fail problem. These are all issues between observations, tensions between observations and theory, which kind of gets at the difficulty of understanding satellite galaxies and why we see so many of them and what their properties should be. Okay, to get at this, the SAGA survey is one of the premier surveys in the local, or basically out to about out to 50 megaparsecs of us, trying to get a spectrum of every single satellite galaxy around, Milky Way analog. And so the goal again is to take a spectrum of every faint pinprick of light that could plausibly be a satellite dwarf galaxy and confirm it, right? And so we're talking about something like 3 galaxies out of 500 targets within, the virial radius, projected virial radius of a Milky Way-like host galaxy, and trying to understand which of those are true satellites. It turns out that with machine learning, you can actually go and spot the differences. In fact, with your eyes, you can probably also spot the differences between low Z galaxies and high Z galaxies. And in fact, that's what we did. We just went to the DESI legacy imaging surveys, found something like, 6 million images of all the plausible candidates and found 100,000 low Z candidate galaxies. So in other words, SAGA is very observationally complete in trying to look at the virial radius of a bunch of low redshift galaxy halos. And we're basically trying to probabilistically infer which galaxies are dwarfs in the low redshift universe. Now, Elise is about to talk about confirmation of some of this in a moment. But I just want to say that we've gone out and pushed well beyond what Sloan Digital Sky Survey is able to do. This is R of 17.78 to here are a bunch of candidates that we found with machine learning. And in fact, we can actually assign those to the confirmed host galaxies as satellites. And so again, these are not confirmed, but we can basically look, again, as a function of magnitude out to like R21, which of these galaxies are likely to be dwarf satellites around those hosts. We can look at individual hosts, which again sort of confirms our expectation that these are what the satellite galaxies look like around confirmed hosts. This is from NSA, NASA Sloan Atlas. And in fact, you can kind of go into different environments or look at different mass ranges than SAGA would otherwise study, which highlights the power of this kind of approach. We're even finding these very red dwarf satellite candidates, which are really hard to observationally follow up. But again, we'll hear more about that in a moment. All right. Did anybody find any satellites here? Well, I don't know. None of these are actually spectroscopically confirmed, but they're probably these two here. If you thought so, then you agree with CNN, so that's all good. All right, really, really quick, 3 shots. So it turns out that we can make the satellite radial profiles as a function, so satellite radial profiles as a function of the host galaxy mass, and try to understand, what are the, how many satellites are in these hosts, and how they're distributed in projection around hosts. So we can see that in its covariant relationship between galaxy mass and galaxy morphology. So this is for disks and ellipticals on the right here. We are also able to say something about the halo accretion efficiency and perhaps something about the too big to fail problem. All right, I have to stop talking very soon. So talk to me more if you want to learn more about this work, and also something that we're about to explore, which is looking at the differences, basically the assembly bias between host galaxies that are in Milky Way M31-like pairs versus at just lone Milky Ways out by themselves. So this is all very scientifically productive. We've also come up with new graph neural network representation of this sort of cosmic web, and we want to compare that against what we're able to pick out using convolutional neural nets. And so again, very excited about all this. Here's my summaries, and I will stop talking now. Thank you.
So hi, time for questions.
Spectra of this thing of assigning spectra to galaxies. Should we expect it to work at all for galaxies that are outside the range set, either because they're dimmer or empirical?
Yeah, that's a great question. Should we expect this method to work outside the training set? And I would say no, like emphatic no. You shouldn't expect it to work. If it's at different redshifts, we know that galaxy morphologies covary with their properties over redshift, and we don't know what that relationship looks like as it goes out of domain. We shouldn't expect it, but when we find out that it does work outside the training set, I think that's also pretty interesting. And so when we look at a galaxy like this one, which is actually not really representative of our training data, like it's way too big. In fact, when we grab an image cutout on the sorts of things that we train on, you just kind of got this little thing in the middle, right? You don't even go out to the spatial extent of those spiral arms. And yet we're able to learn something about its AGN state. So maybe what we're learning about is the sort of thing that, we're basically able to infer something that does stay constant, even though we thought that this galaxy might be an outlier in other ways. Yeah. I think it does work. Yeah, it does depend on the methodology. I wouldn't be super confident about using these for photoses, but I think certain, groups have showed that there is a lot of, you can boost photoses by using morphological information. You can also, co-model the spectroscopic information along with the redshift group, and this is stuff that Peter Melchior and others have done. So I think there's a lot of work that can be done there. I agree. I will say though, that's not something we try to do. We just de-redshift the spectrum, so we cheat. Thanks.
Okay. Yeah, thanks. Super talk. So my general question is, can you get at the correlations or the physical relationships that the CNN is actually kind of picking up on? And just to kind of give an example with your mass metallicity work, so people have shown that the strongest correlation, like along that third axis of the mass metallicity relation, is with gas content. Okay, so I could see a situation where you have like a correlation between morphology and gas content, and then a correlation between gas content and metallicity. And so that if the CNN is like smudging those together and learning those two and combining it, it's a bit less useful to me than if you can pick out the individual relationships. So I was just wondering if you could comment on that.
Yeah, I think that's very insightful. Thanks for that. And indeed, you're right. Like we are able to learn the gas content of galaxies as well from the images. So which is the underlying thing that matters? I believe this is an unsolved problem in astronomical machine learning, but a very interesting one that we should continue to push forward on. ultimately, it really comes down to questions about causality and intrinsic dimensionality. How many variables does it take to explain this, this galaxy? And anytime we compress, things down to like, this is the metallicity within a 3 arcsecond fiber, plop down on the center of a galaxy, subject to the main galaxy sample selection, there's going to be kind of caveats and, a breakdown of the things that are actually physical and the things that end up being observational or elsewise. So I think we need to make a very detailed study in order to answer that question more directly. But I don't think we try to get at that here. But we do know that the morphology is important. And even if it uses a proxy for star formation, for gas content, and other sorts of things, it's a very useful proxy.
I'm gonna do that Kwame thing because I think this is this question and what's happened here over the last 3 weeks and exactly this slide comes together in, I think, a really interesting idea that we've been percolating about here and having now the conference happening. I'd love to like bring the rest of the community in, which is to say, I think a really interesting thing that we should be doing to answer exactly that question is to take what is known as the gas mass for each of these galaxies, take what is known as the metallicity, and take what is known as the stellar mass, predict the metallicity directly from those, and then use the CNN to train on the residuals. Because the question you're asking is, how do I know which one of these is happening? Which one of these is what's happening? And I think there was a point made about the way the Princeton group works, the Princeton Astro Data Lab that you made, thank you, which is that you don't make the network try to learn what you already know. And so if instead of doing what John did here in 2019 and what he and I worked on in 2020, instead we say, well, we know all these things. Let's take the relationship between stellar mass and metallicity. Let's take the relationship between gas mass and metallicity. Let's subtract it out. We already knew that. Now, can the CNN do better? Can the CNN see what's happening spectroscopically in the gas-based metallicity and then use the GradCam technique or saliency technique to figure out which parts of the galaxy are giving us the extra leg up? So Mike and I have been talking about this in terms of how this might be useful. So I think that might be a real key to moving forward here. So sorry for the comment, but wanted to hop in.
Do you have questions on Zoom? Nope. So sorry.
Yeah, just a quick comment. Thank you, John. And I agree with Josh looking at the residuals. I had, maybe the opposite proposal, which is probably stupid, but did you try to just predict the spectra with the photometry, with the synthetic, with the summary statistics, because you said there's a boring table? How much information there's already on the photometry by itself? Yeah. So maybe that will give you some clues about what exactly, is in the images. So.
Thanks. Yeah, no, so we did do that in this paper. We're using GRI band imaging, and from that you end up with a far worse prediction, something of order like 0.1213 dex. Viviana Aquaviva also looked at this using much more information, including, spectroscopically derived information. They basically achieved the same floor that we did, about 0.08 dex. This is using very informative things like U-band and also, spectroscopically derived information. So, yeah, so I think we're getting close to there, but we're learning. Maybe we are getting close to the information content floor of this scaling relation. Maybe there's more to be learned in the residuals. I'm not sure. Yeah. Oh, keep on.
Thanks. How much did you look at the scatter between CNN versus spectroscopy metallicity, and how much smaller than this scatter is that?
Yeah, that's right. So so the scatter between this scatter, by the way, is about 0.1 dex, and then between just the CNN and spectroscopically predicted metallicity, that's like 0.08 dex or 0.085 dex. It doesn't quite add up in quadrature if you think about what the breadth of, the intrinsic mass metallicity relation is, or maybe we should be using some sort of fundamental metallicity relation and try to add those in quadrature. But I think when you do that, you still end up with too much scatter. In other words, the morphology is explaining some degree of scatter, subject to caveats about the covariance between all these properties and things. So, yeah, I think that answers that.
Thanks. So I do have one request for all people who are asking questions. Please say your full name before you ask the question. So I'm Peter Bruzzi. I have a question about domain shift. So with the X-Saga sample, you're training on satellites or close to satellite things around Milky Way galaxies. How do you deal with the domain shift of recovering field dwarfs outside of the real radius?
Yeah, thanks for that. So this is kind of tricky, but so X-Saga actually goes out to about 25 to 40 megaparsecs. That's like the redshift range that they're interested in. We actually look at all confirmed low-Z galaxies, where low-Z is defined as up to about 130 megaparsecs in those fields. So it's probably true that we're biasing the range of environments that is being seen here. Like they might be extending along a filament, sort of back out. But at the same time, we are hoping to get again like another 100 megaparsecs farther in projection. And so X-Saga does definitely have field samples. If you look at like the distribution of all the things that we find, there are indeed things that are sort of out by their lonesome. There are little dwarf pairs that we can find, which are really fun to look at. I think there's a lot of rich follow-up that we can do. Thank you for the question.
One last question while Elise sets up.
Yeah, I think it's time for Elisa. Can we reserve our questions for later, please?
Absolutely. Thank you.
Thanks.